So problem 1C gives us a graph of the mean absolute error of a constant prediction W on our data set. And it gives us these three labeled points, 15, 4, 18, 5, and 22, 7. And it says we are given that there are n equals 72 data points. And the question is, how many data points are exactly equal to 18? The first thing to sort out here is the strange fact that we are given that the data set has an even number of data points, yet there isn't a flat ridge at the bottom, as we saw in the first examples in lecture, in which there are an even number of data points. So why isn't it flat at the bottom? And we know it's not flat at the bottom because this has to be the bottom. The median of the data set is 15. We were told that earlier in the question. And you can see the slope increasing to the left over here. So this is the bottom. Why is it not flat? What this must mean is that the median 15 is repeated. So to give you a smaller example, not with 72 data points, but with 4, like this is an example of a data set with an even number of data points, but the middle two values are both the same, and so there isn't a whole line of infinitely many minimizers. There's just one minimizer, and it would be 15 here. So that's how that's possible. And so what that tells you that 15 may be repeated, or it is repeated, and the question's premise is that 18 is also repeated some number of times. The question is, how many times is it there? So the data set must look something like, a bunch of values and then some 15s. And then the thing after 15 must be 18, right? There are no values in between, because if there were, we would have another kink in the graph, because the slopes only change for this mean absolute error graph at the original data points. So we'll have an 18 some number of times, and then eventually a 22, and then some other stuff maybe too. Okay, so the question is, how many values are equal to 18? The key here is to remember the formula for the slope of the graph of mean absolute error. We can compute the slopes of both line segments here, right? Like using just the information on the whiteboard, I can find the slope of this segment, and I can find the slope of this segment. But if I remember that formula from class, that also tells me what the slope of this segment is, but that relates the slopes of these segments to the number of data points to the left and right of some candidate value of W that I'm looking at. Well, then maybe I can learn something about the inputs into that formula given the information on the graph. But what am I talking about? Well, what's the slope of this first segment between 15 and 18? So if I live here, what is the slope of the line there? What is it? Well, it's the change in y, which is 5 minus 4, which is 1, over the change in x, which is 18 minus 15, which is 3. So the slope of this segment is a third, and similarly, the slope on this segment between 18 and 22 is the change in y, which is 7 minus 5, which is 2, over the change in x, which is 22 minus 18, which is 4. So the slope here is 2 over 4, which is a half. Okay? Now, in general, what is the slope of this graph? At a W that is not the data point, or not a data point, right? So I can't calculate the slope here. It's undefined. Can't calculate the slope here, it's undefined. But at any W that is not an original data point, the slope is the number of data points to the left of it minus the number of data points to the right of it over n. And we know what n is here, it's 72. So what I'm saying is that now we have two ways of calculating the slope of each of these segments. There's the geometric way, which we've already done, and then there's the way using this formula. And when we equate the two, maybe we'll get somewhere. So let's start with the first segment. That is this one, the one whose slope we know to be a third. What is it also? Well, it's equal to the number of data points to the left of my point here minus the number of data points to the right over n. So why don't we introduce a new variable to represent the number of data points to the left of a W that is between 15 and 18, but not exactly equal to either of them. Let's call that L. So L is the number of points to the left of, I don't know, let's just pick a value, 16. Or we can say number of points less than or equal to 15. Okay? That's the number to the left. What about the right? I could make a new variable r, but I know how L and r are related. right? If I'm standing here, everything is either to the left of me or to the right of me. Similarly, I'm looking at the slope of the segment here. Everything is either to the left or to the right. So instead of making a new variable r here, I could just do n minus L, okay, over n. But remember, the question tells us what n is. N is 72. So I can plug in 72 there and 72 there. And here I actually have enough information to solve for L. I'll save that for just a second, but just know that we can solve for L there. Now, what if I apply this same thinking to the second segment, the one whose slope is a half? Well, its slope, using the left minus right over n formula, same n, so we're going to have a 72 there, is going to be the number of points to the left of me here minus the number to the right of me here. What is the number of points to the left of me here? Is it the same L? No. It's related to the same L, but there are more points to the left of me here than there were here. How many more are there? Well, all we've accumulated from moving from here to here is just the number of data points that were equal to 18, right? The only difference between this point and, say, if these are my 18s, this point is the number of data points that were exactly equal to 18. So why don't we let k be the number of points equal to 18? That is ultimately the answer we are trying to find here. The answer to the question is whatever k ends up being. When I'm standing here, the number of points to the left of me is L, which was the number less than or equal to 15, plus k. And the number to the right of me is just n minus whatever that is. So n minus L plus k. Hopefully we can see that okay. All over 72. Now n is 72, so I'll put that in here. Now here I have two unknowns but just one equation, but remember, I can solve for L here. And so when I solve for L here and plug that value in here, that'll give me just one unknown here, which is k, and then I can solve for that and find what k is supposed to be. Okay, so let's do that quickly. Here I need to solve for L. 1/3 is the same as 24 over 72, which means I can just equate these numerators here. So I have 24 is equal to L minus 72 plus L. So I have 24 is equal to 2L minus 72. Adding 72 to both sides gives me 96 is 2L. So L is 48. Okay. Now I just got to plug L equals 48 over here. Using the same logic, a half is the same as 36 over 72. So now I can just equate this numerator. 36 equals, and I'm going to plug in my 48 as L. 48 plus k minus 72, distributing this minus sign, gives me plus L plus k. So that's going to be plus 48 plus k. What can we simplify here? We'll let 2k stay over here. And on the left, I'm going to get a 36 minus 48 plus 72 minus 48. So all of that over 2 is what k ends up being. We can make the math a little simpler by dividing by 2 directly. So this tells me that k is going to look like 18 minus 24, that's minus 6, plus 36, which is 30, minus 12, or minus 24. Which to me looks like minus 6 plus 36, that's 30, minus 24, which is 6. So k equals 6, and we'll end the video at the right time because I'm getting a call.